We just talked a bit about the random walk model, and the random walk model looks like this. It's the value of the y variable, which is explained by its own lag, one term lag, or one period lag, plus the error term. And this is the simplest model of a process which has a stochastic trend. And the error terms, they are assumed to be identically and independently distributed, and the expectation of the error term is 0, no matter which value the lags do have. And this random walk model can actually teach us about stochastic trends. So we can see several key points, and we can look at the expectation of y, or before we look at the expectation, we can look at that yt is equal to yt minus 1 plus the error term, right? And if we take the expectation of both sides, then we get the expected value of yt given information about yt minus 1 and yt minus 2 and earlier lags is equal to the expectation of yt minus 1, which is the one period lag, given the value of the lags. And remember, or just note, that this expectation of yt minus 1 is given with the information of yt minus 1. Okay, so you already know the yt minus 1 value here. And this is also, this is added with the expectation of the error term given the value of the y variable at time t minus 1 and time t minus 2 and so on. And we know that the expectation of the error term given any lags is equal to 0, right? And so this is equal to 0, and this is equal to yt minus 1, because the expectation of the stock price today or yesterday is given information about the stock price yesterday and the day before that and so on, is the price of the stock yesterday, right? So this means that the best forecast for yt is actually yt minus 1. So the best forecast of the next period value of yt is its previous value. And this process is not stable. It fluctuates, right? And that's because the error term is on average 0, but it's drawn from a distribution such that you get this kind of we say stochastic process, because it's changing at random, so to speak. It is important to notice that even though we have the y variable, we have time here, if we start the process here, and we draw these error terms, and the error terms defines the movement of the process, and it's random. This is just one instance of that process. If we started that process again with and drawing the error terms, then we would get something like this maybe, or something like this, or something like this, or and you get the point, right? So every time you start the process again and let it run, then it kind of moves at random, right? But the expected value, if you're at t equals 0 here, and you would predict the value at t equals 10 here, then you would just predict like a flat line here, because this error term is what is driving the process, and the expectation of the movement up or down is on average 0. So you could expand this model by adding a constant. So in the previous model, you did not have this constant, and this constant is actually a drift term. So this helps us to model the tendency of a series to move in one direction. Okay, so let's say that yt minus, let's see, I can write that properly, yt minus 1 equals 100. Okay, so this is, for example, a stock price, and we have here that t equals 0, and we have 100, right? And what is the price at yt? Well, it's this 100, right? So yt equals 100, which is yesterday's price, plus a drift. So every single period you add the drift term. Okay, so maybe this drift term is €1 per month or something, or and you add the error term. So this drift will actually cause the expectation of the, let's see, this was a horrible drawing. Let's see if we can get this more horizontal. Okay, so this drift, if you did not have the error term, then this drift would kind of make this process go upwards. So this is the expectation. So this is the expected movement of the process. For example, the stock price. If you're standing at time 0 and the price is 100, okay, and here is maybe 10 months ahead. Sorry, and in the previous model, you did not have this drift term, so in that model, you would just assume or expect a constant value, right? But with the drift term, you would get these random, because of the random error term, you would get these random processes around this kind of mean. Okay, so the mean is drifting upwards. So this fan-shaped pattern that you often get from the random walk model is now upwards sloping. Whereas in the random walk with drift, then you would get this fan-shaped pattern centered on the constant value of the process at time t equals 0, the start of the process. So this beta term is really the change in the average or the expected value per period. A quite important trait of the random walk is actually that it's non-stationary. And we can see that it's non-stationary because we can take the variance of the random walk at time t, and we can split yt into yt minus 1 and the error term, right? Because we had that yt equals yt minus 1 plus the error term, right? This is the random walk without drift. So, if we take the variance of both sides, then we get the variance of yt equals variance of yt minus 1 plus the variance of ut, which is the error term. And we can do this because we assume that the variance of yt minus 1 and the variance of the error term, they are not correlated. So if we if yt as a process were to be stationary, then we would have a constant variance, right? And we can only have a constant variance if the variance of yt is equal to the variance of yt minus 1. But if these two are equal, then the variance of the error term has to be 0, which is not a stochastic trend. Then you would, if this variance of the error term was 0, then you would just have a constant process where the value of yt is equal to the value of yt minus 1, which in turn creates variance, or causes the variance of yt and the variance of yt minus 1 to be 0 in itself. So it's impossible to have a random walk which is stationary with a constant variance. If we look at the variance of the random walk from a different perspective, we can just suppose that we start the process at 0, right? So we are here, and we have t here, we have y equals 0 here, and y. Okay, so we start off at 0, right? And then the next value, because yt is equal to the value of yt during the previous period plus an error term at time t, right? So y1 is equal to the value of y during the previous period, which is 0, and plus the error term, which is which is the error term at time 1. So y1 is 0 plus an error term, right? And then we go to the next time period, and y2 is equal to the value of y during the previous time period, which is just u1, and you add on the error term for time 2. So y2 can be thought of as the sum of the error term for time 1 and time 2. And these error terms, they add up, so y3 is equal to well, this should not be there, is equal to the value of y during the previous period, which is u1 plus u2, and you have to add on the error term for period 3, which is u3. So here you have sorry, here you have the value of these processes, or the y variable is increasingly dependent on sums of the error term. So the value at yt is just the sum of all the error terms from t equals 1 to t equals small t. And if we take the variance at each step, then this variance here, variance of y0, is equal to 0, because we know the value. So there's no variation here. But the variance of y1 is equal to the variance of the error term, right? Because the value of y1 is the error term. And the variance of y2 is just the variance of u1 plus u2, okay? And because these error terms are uncorrelated, then you can split this into the variance of u1 plus the variance of u2, right? And you can assume that the variance of the error term is constant, which means that if the variance of u equals sigma squared, then you can just add up sigma squared plus, or this would just be sigma squared plus sigma squared, right? So this would be 2 times sigma squared for the second period. So, not that one. You use the, is it possible? My pad has slipped. So here we go, and we have this. Okay, so this is because of constant variance of u. Okay, which means that we have our result, the variance of our process is equal to the variance of the sums of the variances, which means that we can just add them up. So we have t times sigma squared variance in the period of t. And you can see that from the fan chart, because at time 0 you know the value of the process. At time 1, if you do this repeatedly, then you would get something like this, right? But at time 2, every process here could go further out, and you would get this fan-shaped process, and you see that you get like this fan processes, right? So the variance of the random walk process is increasing linearly with time. The random walk model is a special case of the AR1 model with beta equals 1. Okay, so if we just have the yt equal to beta, beta times the 1 period lag plus u, then we have we can immediately see that if beta equals 1, then we have the random walk model. And what we know about the random walk model is that it's non-stationary. But if the beta is less than 1 in absolute values, which means that it's between -1 and 1, not including 1, then we can say that yt is stationary. And why can we do that? Well, it's because if we have y here and t here, then if beta equals 1, then we have this fan-shaped pattern, or what do you say? Yeah, we can call it pattern of increasing variance, right? But if this is beta equals to 1, but if we have t here, y here, and the absolute value of beta is less than 1, then if your process is here, then you would and this is 0, then without any movement in the error term, or without any shock from the error term, then you would expect this process to taper off, right? To get close to 0. And which means that you have this force which draws the process closer to zero. But because we have this this shock from the error term, then the process will not get exactly to zero, but it might come close to zero because every time it's close to zero, another shock in a random direction and random magnitude comes, and you will have this process which is quite stable in its variance around the mean of zero. So this is why we can say that if the beta coefficient is below 1 in magnitude, in absolute magnitude, then you have this force which limits how far away from the average this process can go. So then this means that it's the process is stationary, whereas the random walk model is non-stationary. In the random walk model, we saw that if the beta coefficient on the lag variable is below 1 in magnitude, which is between but not including -1 and 1, then the process is stationary. And more generally, if you have p lags in your model, then stationarity is linked to the roots of the polynomial. So the roots of this polynomial would be the values of z, which makes this equation equal to, or these terms equal to 0. So if the roots are greater than 1 in magnitude, then this process is stationary. And you see the coefficients here are from the regression that you make. So you can just type in this 1 minus and then the regression coefficients and the terms here, and make, for example, Stata solve this this equation and give you the roots. And for the math savvy of you, it's enough that the roots are outside of the unit circle in the complex plane. This means that if at least one root of the autoregressive function with p legs equals 1, then the series is actually said to have a unit root. And if the process has a unit root, then it contains a stochastic trend and is non-stationary. And we saw that, well, if the process is non-stationary, then we will have quite a few problems with our regression model. But if the roots are greater than 1 in absolute value in the complex plane, then yt is stationary, and it does not contain a stochastic trend. And because we can, because yt does not have a stochastic trend, or if it does not have a stochastic trend, then we can trust our model inference. So we can perform hypothesis test, and we can make predictions with our model. And this is why we often use stochastic trend and unit root interchangeably. So some people talk about unit root, and other people talk about stochastic trend, but they are really just the same kind of process. To get a grip of this idea behind the root of the equation, we can take a look at the autoregressive lag1 model of order 1. And what is the root of this process? Well, you have the yt equals beta 1 times yt minus 1 plus the error term y or ut. And what is the root of this this equation? It's actually the value of z, which solves 1 minus the beta 1 times z equals to 0. Because you can just move this term over to the other side, and then you have the difference between these two terms, or of which you would like to find the root. And this means that if you move the this over to the other side again, and you divide by beta 1, then you can find the root of the equation, which is equal to 1 divided by the beta. So this is the root. And when is this process stationary? Well, for the autoregressive process to be stationary, the root must be greater than 1 in absolute value. So when is this term 1 divided by beta 1 greater than 1 in absolute value? It's when the beta is actually below 1 in absolute value. So this occurs when 1 is greater in absolute value than the beta 1. And this is what we mentioned in point 4. If we get to point 4 above. And the reason why we are not testing for beta greater than 1 is that if beta is greater than 1, then we have a so-called explosive process, which is by definition non-stationary. Yeah, so this is how you calculate the root of the AR1 model and test whether, or get an idea if the root is such that the autoregressive model is stationary.